Hi students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as magnetic effect of electric current. We're going to see the working of tangent galvanometer today. TG. It's referred to as TG, tangent galvanometer. Now, we had seen the construction of tangent galvanometer when no current flows through the coil. When suppose if there is no current flows through the coil, in that case, when there is no current flowing through the coil of the galvanometer, then the horizontal component of the Earth's magnetic field acts on the coil, and therefore the needle would remain in north-south direction. When no current flows through the coil, the horizontal component of Earth's magnetic field acts on the needle. Horizontal component of Earth's magnetic field, we refer to this as BH, acts on the coil, and therefore the needle remains in north-south direction. Basic law. Any freely suspended magnetic object or magnetic needle is going in north-south direction. That's exactly what's happening here. Why? Because of the Earth's magnetic field. Now, when current flows through the coil, when current I flows through the coil, now if current I flows through the coil, it is going to produce a magnetic field, right? When current flows through the coil, it will produce a magnetic field. So when current I flows through the coil, it produces a magnetic field, right? Yes, it will produce a magnetic field at the center of the coil because it's a circular coil. Now this magnetic field that it will produce at the center of the coil is going to be at right angles with the plane of the coil, the center of the coil, which is right angle with the plane of the coil, right? That is, if it is at right angle with the plane of the coil, that means it will produce in east-west direction. That is east-west direction, right? Now let's assume that if R is the radius of the coil and N is the number of turns of the coil, if R and N are the radius and number of turns of the coil, then the magnetic induction B at the center of the coil, the magnetic induction B at the center of the coil is given by V is equal to mu 0 Ni upon 2R. That will be the magnetic induction. B is equal to mu 0 Ni upon 2R. So thus this is the magnetic field that the needle will experience when the current is flowing through the coil, right? So the magnetic needle under the influence of the two magnetic fields. Now there are two magnetic fields that are going to act on it, two magnetic fields B and BH. There are these two magnetic fields which are going to act on it. The magnetic needle is under the influence of two magnetic fields B and BH which are at right angles. Right? Hence, the needle deflects through an angle theta. Needle deflects through an angle theta. Right? Now, since there are two magnetic fields and they are perpendicular to each other, I can use the tangent law. If I use tangent law, I can say that B is equal to BH tan theta. That's what my tangent law says. But B we already found out as mu 0 Ni upon 2R is equal to BH tan theta. Right? In which case I can therefore say I is equal to 2R BH upon mu 0 N into tan theta, out of which 2R, that is the radius, the horizontal component of magnetic field, the permittivity and the number of turns are going to remain constant. So I can say that let 2R BH upon mu 0 N be equal to K. Therefore I will be equal to K tan theta. So the current is directly proportional to the deflection, right? Now where K is called as constant, I can say where K is called the reduction factor. Of the galvanometer, right? So thus I can say that I is directly proportional to tan theta. Thus for a tangent galvanometer, the deflection is directly proportional to the current, right? And that's how the galvanometer is able to measure the current. Fine, do we get this thing here? Next, let's try to find out the sensitivity and accuracy of a tangent galvanometer. Right, let's try to find out sensitivity and accuracy of a tangent galvanometer. Now we've already done this, right? The galvanometer is said to be sensitive if it gives large deflection for small current passing through it, right? Thus, the sensitivity of a tangent galvanometer is expressed in terms of the ratio d theta upon di, right? How much is the deflection it gives per unit current, right? Now for a tangent galvanometer, we have just derived that I is equal to K tan theta, right? Now in that case I can say differentiate this equation. If I differentiate with respect to theta, so I'll get d by d theta of I is K times d by d theta of tan theta, which is nothing but sec square theta. So in which case I can say that di is K times sec square theta into d theta, cross multiply again, therefore I can say d theta upon di is 1 upon K sec square theta, right? But 1 upon sec square theta is cos square theta, so d theta by di is cos square theta upon K, Fine, do we get this thing here? So that is going to be my sensitivity of a tangent galvanometer, right? Now, from this equation it is very clear that if I want the galvanometer to be more sensitive, the value of K should be as small as possible, right? K and sensitivity are inversely proportional to each other, right? K is sensitivity, that is d theta by di, is inversely proportional to K, right? Thus, so I say what? That I can say that K is equal to, we have already derived the value of K. We've said that K is equal to 2R BH upon mu 0 n. Thus, I can say that the sensitivity of a tangent galvanometer can be increased by, it is inversely proportional to K, so by reducing the radius. If I decrease the radius, the sensitivity will increase. By decreasing the value of horizontal component of the Earth's magnetic field, and by increasing the number of turns. So that's how you change the sensitivity of the tangent galvanometer. The sensitivity of the tangent galvanometer can be increased by reducing the radius of the coil, by reducing the horizontal component of the Earth's magnetic field, and by increasing the number of turns. Fine, do we get this thing here? Now, once we've done sensitivity, the next thing is accuracy. Now, when current flows through the coil, when current I flows through the coil, I can say that I is equal to 2R BH upon mu 0 n cos theta. We've just derived this, right? Now, there is the accuracy of a tangent galvanometer depends upon the accuracy in the measurement of current, which in turn depends upon the accuracy of R and theta, right? Now let's assume that the d theta is the error in the measurement of theta. Let us assume that d theta is the error in the measurement of theta. Caused by causes an error di causes an error di in the measurement of current. Right? So in that case, I can say that for a tangent galvanometer, I can say I is equal to K times tan theta, differentiate with respect to theta. If I differentiate with respect to theta, I'll get di by d theta. You'll get di by d theta is equal to K. Tan theta can be written as sec square theta. So I can say di is equal to K times sec square theta into d theta. Right? Call this as equation 2. Right? Call this as equation 1. Right? Your I is equal to K tan theta, call that as equation 1. Now divide equation 1 and 2. If I divide equation 1 and 2, I'll get di upon I is K sec square theta d theta upon K tan theta, right? So in which case I can say that di upon I, K is gone, sec square theta is nothing but 1 upon cos square theta. Tan theta is nothing but sin theta upon cos theta into d theta. So you will get cos and cos gets cancelled, so you will get di upon I is d theta upon sin theta cos theta, multiply by 2, divide by 2. Why did I do that? So that I could use my multiple submultiple formula. So I can therefore say that di by I is 2 d theta, 2 sin theta cos theta is nothing but sin 2 theta, right? So thus it is very clear from this equation that the measurement of the current the error in the measurement of current is minimum when 2 theta is maximum. This is your, therefore I can say that error in measurement of current is minimum when 2 theta, sin 2 theta is maximum, because sin 2 theta is maximum because from the equation we can clearly see that di by I is inversely proportional to 2 theta. So di by I will be minimum when 2 theta will be maximum, but the maximum value, but sin 2 theta maximum value is 1. The maximum value that sine function can take is 1, right? Now sin 2 theta is 1, therefore I can say that 2 theta has to be 90 degrees, because we know that sin 90 is 1. If 2 theta is 90 degrees, that means I can say theta is 45 degrees. That means the accuracy of a tangent galvanometer is maximum when the deflection is near 45 degrees, right? Therefore, while using a tangent galvanometer, the observations are taken when the deflection is near 45 degrees, right? Because at that point of time the accuracy of the tangent galvanometer is maximum. Fine, do we get this thing here? So here we've seen how we can get very accurate measurement by changing the current. Now let's also find out that there is an error. Let us assume that dr is the error in the measurement of radius. Let us assume that dr is the error in the measurement of radius and causes an error di in the measurement of current. Right? Now again let's start for a tangent galvanometer. For a tangent galvanometer, we know I is nothing but 2r bh upon mu 0 n tan theta. Right? Now differentiate with respect to r. Now if I differentiate with respect to r, I'll get d by dr of I is 2r bh mu 0 n tan theta into, because all the terms are constant, right? So in that case you will get this as, you are differentiating, you have 2r, so this will become 2, d by dr of r is 1, right? So in which case I'll get di is 2bh upon mu 0 n tan theta dr, right? Once you have this, divide this equation, let's call this as equation 2, let's call this as equation 1, divide equation 1 and 2. If I do that, I'll get di upon I is 2bh mu 0 upon mu 0 n tan theta dr upon 2r bh upon mu 0 n tan theta. So 2BH gone, 2BH gone, mu 0 and gone. So what you get is di upon I, tan theta gone is nothing but dr upon r. Right? So thus for minimum error in current, the radius of the coil must be as large as possible. Here you can see that error in current is inversely proportional to radius. I can therefore say for minimum error in current, R should be as large as possible. Fine, do we get this? Thus, from this we conclude that the requirements for better accuracy of a tangent galvanometer are: the deflection should be 45 degree, the radius should be as large, and you should have small number of turns. Right? So I can say that requirements for better accuracy one, deflection near 45 degrees. Second, large radius. And third, small number of turns. Smaller number of turns. If these three conditions are fulfilled, you will have very high accuracy and sensitivity in the case of a tangent galvanometer. Right? Let us compare a moving coil galvanometer with a tangent galvanometer. Compare moving coil galvanometer with tangent galvanometer. Now between the two, a moving coil galvanometer is more sensitive than a tangent galvanometer. A moving coil galvanometer is more sensitive than a tangent galvanometer. Right? The sensitivity of the moving coil galvanometer can be easily increased without losing the accuracy. But here in the case of a tangent galvanometer, if I want accuracy, I have to increase the radius. And if I increase the radius, I will lose the sensitivity. A tangent galvanometer will be more sensitive if the radius is as small as possible. A tangent galvanometer will be more sensitive. A tangent galvanometer will be more sensitive if the radius is as small as possible, and it will be more accurate if the radius is as large as possible. So here in the case of a tangent galvanometer, if I want more accuracy, then I have to sacrifice sensitivity. But that is not the case in the case of a moving coil galvanometer. So I can say that the sensitivity of a moving coil galvanometer can be increased without losing accuracy. In the case in tangent galvanometer, if sensitivity is increased, then its accuracy decreases. Right? Next, the moving coil galvanometer does not require any presettings, while tangent galvanometer requires presettings in the magnetic meridian. because it depends upon the Earth's magnetic field. Hence, it has to be set. It has to be preset in the magnetic meridian, right? A moving coil galvanometer does not require any presetting while tangent galvanometer requires presetting in the magnetic meridian. The deflection of the tangent galvanometer can be easily affected by stray magnetic fields, but in the case of a moving coil galvanometer, stray magnetic fields do not affect the deflection because it has its own very strong magnetic field. A tangent galvanometer depends upon the Earth's magnetic field and the magnetic field produced by the coil. Hence, a stray magnetic field can easily affect the deflection, which is not the case in moving coil galvanometer. Right? The deflection of a tangent coil galvanometer can be easily affected by stray magnetic field, right? But a moving coil galvanometer has its own strong magnetic field. A moving coil galvanometer has its own strong magnetic field and is not affected by stray magnetic fields. Fine. Now, the current in a moving coil galvanometer is directly proportional to the angle of deflection and hence it is linear, whereas in the case of a tangent galvanometer it is directly proportional to tan theta, tan of the angle, and hence it is not linear, right? Current in a moving coil galvanometer is directly proportional to theta and hence its scale is linear. Current in tangent coil galvanometer is directly proportional to tan theta and hence its scale is not linear. Done? Okay, we'll stop this here for the day. Thank you very much.